Here in 17.2, now we'll actually look at a little bit of the numbers that go on the normal curve and like how we're going to use this as a measuring stick for data. So normal curves started with a German mathematician, or was one of the biggest contributors, so it gets to be a little bit named after him, mathematician Carl Gauss. And so sometimes you hear people say Gaussian curves, but that's the same thing, so normal curve. And they're all kind of, or a bell curve. And technically, when people talk about curving grades, this is where that word came from, but usually they're not actually curving grades because that would mean that we were doing it competitively. So it doesn't matter if this is a 70 or 100%, it matters if you did better or worse than other people. And so when people just say, well, I'm going to curve this by adding 10 points to everybody, so it's not actually a curve. But this, if we distributed all the grades so that the most people got C's, a few people got A's, a few people got E's, if we distributed it perfectly, that would be a true curve. Usually very few scenarios where you want to do that, but that's where the idea of that came from. Just adding random points isn't actually curving anything. Mathematically speaking, they all have the same shape. So if we change the axis, so if we're measuring, from 0 to 100 and we make our scale 0 to 100 or 0 to 1,000, you can make the shape look a little bit different. And how wide they are depends on the standard deviation, because that's telling us how spread out it is. But if you mess with the scale, you can make them all kind of look the same, but they all generally have that same symmetric middle curve shape. The symmetry you're actually going to use a lot when we start putting numbers on this. If you know something about the right-hand side of the curve, in fact, we'll look at it here. If you know something about the right-hand side, you know something automatically about the left-hand side because it is perfectly symmetrical. So if you go, say, +1 over here, it'd be the same distance as going -1 over here. It's perfectly symmetrical around the mean. And so the center is where the mean is. And so same thing I was just saying, the center is the mean. And so also what does that mean if it's the center? It means half the data is here and half the data is here. So say if this was test scores, there were 100 people in the class, 50% of people did better than the mean and 50% of people did worse than the mean, which also means the mean then is approximately the same as the median, because the median is is the middle number, right? Half are on the top and half are on the bottom. And so here, the mean in a normal distribution is approximately equal to the median, since it's the middle of the data also. And then standard deviation, we're going to use a ton. If we measure the spread, so to go 1 or 2 or 3 standard deviations away from the mean, says if somebody did way better or way worse than the mean, which is where most people, or 50% of people, scored better or worse than. So the standard deviation is kind of like our distance of steps we're taking, or a little building block of this. And then one thing they want to show you about where they're getting standard deviation on a normal curve. So if they took a wire and they were bending it down and they started bending it upward, there's this point right here in the middle. Also, you can kind of look at it as, see how here it's getting steeper and steeper and steeper and steeper? Then there's a point right about here where instead of getting steeper and steeper, it starts to get less steep. So that's called the inflection point. And so the inflection point is the location of the standard deviation. It's or the standard deviation is the distance from the middle of there. So let's say, like if the middle is, I don't know, 100, and this point happens at 30, then that tells you that your standard deviation is 30. It's the distance from the mean, which is the middle, to the inflection point. And then because we talked about that symmetry, if this is a distance of 30 units away, this one is a distance of 30 units just in the other direction. So it's perfectly symmetrical always. Okay, and then one other important number we'll end up talking about a bunch is Q1 and Q3 are first and third quartiles, the worst 25% of the data like we did in the other ones. So on a standard deviation kind of situation, like if I draw a normal curve down here, probably not very well. Okay, and then we'll say here's the middle, so the mean. And then if I want to think about those inflection points are always one standard deviation away. So let's say the inflection points are right about there. And over here it's right about here. Okay, so the distance from here to here is one standard deviation. So we'll see later when we get our 90, our 68, 95, 99, 7 rule, our percentages of where stuff falls. We'll see that the distance from here to here is about 34% of the data falls in this area here. And so picture if you wanted to split off the first and last 25%, if you went this far, you went too far, because this is 50%. Right, the mean splits off the top, so all of this data here represents 50% of the data points. And we'll see later, this in here is 34% of the data. So if I go all the way from here to here, see how I know I've already gone past the third quartile? Because I'm up to 84% of the data. And so you can kind of eyeball, if that's 84% of the data, what if I only wanted to go to 75% of the data? Well, here's 50, so I know I have to go further than that. And here's 84% of the data, so I know I can't go that far. So kind of somewhere in here is where I should stop if I just wanted to be looking at, I'm just using different colors so you can try to see which scribbles are which. So 75% of the data. If I wanted to know what splits off the bottom 75 from the top 75, which is our definition from those other sections of Q3. So how do I split off the top 25% from the bottom 75%? So just eyeballing it, I can tell I don't want one whole standard deviation, but I definitely don't want to be back here at the mean. And so what they're telling you here, important number to keep in your mind all the time, is here's exactly how far to go. You don't go one whole standard deviation, you go 0.675 standard deviations. So halfway isn't enough. Half a standard deviation wouldn't be far enough. It's like 67.5% of one. So if I say, well, 0.675 standard deviations away is the distance that would get me up to that 75% thing. And so here, this is where the formula comes from, but I definitely always like to draw them if I can, just because it's nice to see what you're looking for. So if I have a curve, and there's the mean in the middle, if I want to go, hey, split off 75% of the data, I go to plus 0.675 standard deviations away from the mean. And so see how this one, it kind of makes sense. It would be plus. You have to go a little further to the right to capture more data. And then, because these are perfectly symmetrical, if I wanted to split off the bottom 25% from the top 75%, I would go 0.675 standard deviations below the mean. And so once you find, hey, I don't want to take a full standard deviation, I don't want to take a full step, I want to take 0.675 of a step. And so you do that in both directions. And so that gives you Q1 and Q3. And also nice, just another thing, thinking about the symmetry, if that splits off 25% of the data, like if this is the bottom 25%, and I know that this is 50% because it's perfectly symmetrical, that means between here and here there must be 25% of the data, and between here and here there must be 25%. So this splits it into perfect quarters. So say if this was a test and there were 100 people taking the test, 25 people scored between the lowest score and here, 25% of people scored between here and the median, 25% of people scored between here and here, and 25% between here and here. So Q1 and Q3 and the mean/median split it into quarters like that. Okay, so then let's look at one. We'll say we have a big sample set, like 1.5 million people almost, and the mean is 100 and the standard deviation is 15. So if we wanted to split it into quarters, could you just go straight to the formula? Absolutely. Is it way easier to see what you're doing if you label some? Definitely. So let's say the mean is 100, so that's right here in the middle. And so if I go a whole standard deviation, like let's say this is that inflection point, I know that this is 115 because the standard deviation is 15, so it would be 15 away. And let's say that this is the other inflection point, and this would be at 85 because it's got to be one standard deviation less than the mean. Okay, but what if I wanted to split it into quarters? What if I wanted to find the Q1 and the Q3? So I know it's not a full standard deviation, it's just 0.675 of a standard deviation. So what's 0.675 times 15? I think is 10.125. And so here, if I wanted to know where's Q3, I don't take a whole step of 15, I only go 10.1 away, so let's round and call it 110, mostly so I could fit it in here. And then on this side, same thing, I don't take a whole step, I take 0.675 of a step, and so Q1, if I subtract 10.1, it'd be like 89 point something, so about 90. Just if I'm rounding. So what I did using Q1 and Q3 is said, okay, well, let's say this is a test or something. The median or mean score is 100. 25% of people did worse than 90. 25% of people got between 90 and 100. 25% of people got between 90 and or 100 and 110. And 25% of people did better than 110. So Q1 and Q3 split it into quarters, but I think as far as the formula goes, definitely easier to see when you write it on here that this is, 0.675 of a standard deviation is 10. So you go plus 10, and on the other side you go minus 10. And so here's the same thing, just not rounded so much, about 90 and about 110. Okay, and then they'll also talk about turning these from standard z-scores into your actual data. So here we were using our raw data saying, oh, the middle is 100 and the standard deviation is 15. On the standard one you see in a lot of books, they make the middle 0 and they make the standard deviation 1, just to make the numbers work out nicely. So if you want to switch yours from one to the other, so let's say I want to get a z-score for the data we just used, let's say the test. So on our test, we had a mean of 100. Oops. Write down the wrong symbol. We had a standard deviation of 15. So let's say I got a 130 on the test. I want to know, is that good or bad? So that's my actual data point. To turn it into a z-score, I do z is how I did minus the mean. So I'm saying how far off of the mean was I. So it looks like I was 30 above the mean, and then divide by 15, so how many standard deviations is that? And so I turn my data point into a z-score. Why is this useful? Well, someone else can look at this without knowing the mean or the standard deviation, and they could say, oh, 2. A z-score of 2 means that you did 2 standard deviations above the mean. And so if we're picturing, if the standard deviation was 15 and 100's in the middle, that probably makes sense. 115 would be here, and we got a 130, and so we were 2 standard deviations above the mean. So that's what z-scores tell you. You can also have negative z-scores if you did worse than the mean.